Hello everyone, welcome to my channel. I already published a blog post about AI agents versus agentic AI, and today I noticed a research paper about this topic, so I thought of creating a podcast using Google NotebookLM. Let us listen to that podcast now.
You know how everyone's talking about AI lately? It feels like it's everywhere.
Oh, absolutely. It's definitely the hot topic.
And two terms keep popping up that sound, well, almost the same. AI agents and agentic AI. It kind of makes you wonder, what's the actual difference?
Yeah, that's a really common question, and it's exactly what we're going to try and figure out for you today.
Okay.
Welcome to the Deep Dive. This is where we take interesting sources, listener suggestions sometimes, and really dig into them.
Get to the bottom of it.
Exactly.
Okay.
And this time we're looking at a research paper. It's called AI Agents versus Agentic AI, a conceptual taxonomy, applications, and challenges.
Right. Sounds a bit academic, but the goal is simple. Yeah.
Totally. We want to give you a clear picture of these, fast-moving technologies.
So think of this as your quick guide. We want you to understand what AI agents and agentic AI really are, what they can actually do, maybe where they're headed.
And our mission really is just to make it simple and clear. No super confusing tech talk.
Cut through the jargon.
Precisely. We want you to walk away feeling like you've got a solid handle on the main differences, what each one is capable of, and, how they're actually being used out there.
We'll skip the heavy stuff, focus on what matters.
Right.
And hey, before we jump right in, just a quick heads up for you. If you're finding this interesting and maybe want to learn even more about AI, the folks at rogermanicum.com have a really great AI course.
Oh, yeah?
Yeah, and you can actually get a special discount. Just use the code QPT. We'll mention it again at the end, don't worry.
Good to know.
Okay, so AI agent, agentic AI. Where do we even begin to unpack this?
Well, sometimes to see how far things have come, it really helps to look back a bit.
Makes sense.
Even before ChatGPT sort of exploded onto the scene, late 2022, the idea of machines doing things on their own, well, it wasn't entirely new.
Right, there were earlier forms.
Yeah, it came from areas like multi-agent systems, MAS, they call it.
Yeah.
Think of that as like groups of simple programs working together. And also expert systems. Those were attempts to kind of copy what human experts knew in a specific field. These were, the early steps.
So like the really early versions of things that could, do a little bit of thinking. What kind of stuff were they doing back then?
Exactly, yeah. You had researchers like Castelfranchi thinking about how individual actions could somehow lead to cooperation. And Ferber, he came up with ways to describe these multi-agent systems, focusing on things like how independent they were, what they could sort of perceive, and if they could talk to each other. These early setups were really about exploring how maybe simple bits of intelligence could create some kind of group behavior.
But these weren't really the AI agents we hear about today, were they? They must have been quite different.
Oh, completely different, yeah. Those older systems, they followed very strict, predefined rules. They couldn't really do much on their own, very limited autonomy.
Right.
And they weren't great at dealing with anything unexpected, minimal adaptability. They mostly used something called symbolic reasoning.
Which is like?
It's like following a very, very precise set of logical steps. Or, even simpler, they just followed pre-written instructions, like a script.
Okay. Can you give me some simple examples, just so I can picture this better?
Sure. Imagine an expert system like MYCIN. It tried to diagnose illnesses, but it did it by asking a doctor a series of yes-no questions based on this fixed set of medical rules it had.
Okay, very structured.
Very. Then you had robots like the Stanford cart. It would move around a room, but basically just reacting to what its camera saw based on really simple programming. Multi-agent systems were used for things like automatically selling off extra resources using online auctions, kind of basic automation,
right.
Even in old video games,
Yeah.
The AI for the enemies. It just followed a set of simple if-then rules. If player is close, then shoot, that kind of thing.
Yeah, I remember that.
And there were also things called BDI architectures, belief, desire, intention. They were used in more complex simulations, like modeling how air traffic controllers manage planes, but still quite rule-based.
Okay, so these sound more like really detailed programs just following orders, not really learning or creating.
Exactly. That's the key difference.
Right.
What were they missing compared to the AI we see now?
Yeah.
Well, the big things were the ability to generate new things, like writing original text or designing images from scratch, and the ability to learn from new information and actually adapt to different situations. They didn't have that deep learning power or the massive amounts of data modern AI uses.
Right. So then, boom, ChatGPT arrives in November 2022. And it's like a switch flipped, wasn't it?
Totally. That release was a huge turning point. Suddenly, everyone was talking about AI that could generate text that felt surprisingly human.
Yeah.
And the research paper we're looking at, it talks about sort of two main stages after this big shift. First, we saw what they call generative agents.
Right.
And then came the things we're focused on today, AI agents and agentic AI.
Okay, walk me through that. What exactly are these generative agents? That sounds like the tech behind ChatGPT, right?
You got it. Generative agents are systems built using those large language models, the LLMs we hear so much about. Their main job really is to create new content based on what you ask them the prompt.
So text, pictures.
Yeah, text, images, computer code, music, pretty much anything you can prompt them to do. Think of tools like GitHub Copilot helping programmers write code faster. Or Jasper AI writing marketing copy, or Midjourney making those amazing images just from text descriptions. These really took off in 2020.
So they're brilliant at making things, but they still need a person driving, telling them what to create next.
Precisely. They react to your instructions, your prompts, but they don't have their own internal goals or the ability to, say, take multiple steps to solve a complex problem all on their own.
Right.
And that's where AI agents come in as the next step.
Okay.
They build on that ability to generate content, but they add more capabilities. Like the ability to use other software tools, make specific requests to other systems function calling, and importantly, think through a sequence of steps.
Okay. So they can handle more complex tasks by themselves.
Exactly. They can manage multi-step workflows autonomously.
Yeah.
Systems like AutoGPT and Baby AGI were early kind of famous examples of this idea.
Okay. So an AI agent can not just create, but also take action using tools. So how does agentic AI fit into this picture then? Is it just more agents?
It's more than just more agents. It's about how they work together. Agentic AI is kind of the next level up in complexity.
Okay.
These are systems where you have multiple, often specialized AI agents collaborating, working as a team towards shared objectives.
Oh, like a team.
Exactly. They need structured ways to communicate, they need shared memory or knowledge, and they might even have dynamic roles who does what can change depending on the task.
Interesting.
Crew AI is an example the paper gives of a framework for building these kinds of collaborative systems. And the potential applications are in really complex areas like robotics, managing intricate logistics, or helping humans make big, tough decisions.
Wow, okay. This sounds like it's getting really sophisticated really fast. The paper even mentioned Google searches, right? What did that show?
Yeah, figure 1 in the paper is quite telling. It shows this big spike in worldwide Google searches for both AI agents and agentic AI, starting pretty much right around November 2022.
So right after ChatGPT.
Exactly. It really highlights how much interest, both from the public and experts, just surged once these powerful language models became widely known and people started thinking, okay, what else can we do with this?
Okay, so we've traced the evolution a bit. Let's really nail down the definition. In simple terms, what is an AI agent?
Right. So the paper describes AI agents fundamentally as software entity programs. They can act autonomously on their own to achieve specific, defined goals within some kind of environment, usually digital. Think of them as being able to perceive inputs, see what's happening, reason about it, figure out what to do, and then take actions to get to that goal. Often they're acting as sort of surrogates for humans in these digital tasks.
So crucially, not just following a rigid script like those older systems, but actually making some decisions along the way.
Exactly. That's a key distinction from just deterministic automation scripts. AI agents have what the paper calls reactive intelligence. They can respond to changes, and they have some perhaps limited adaptability.
And where are we seeing these pop up?
You're starting to see them adopted in places like online customer service chatbots, as personal productivity assistants for information retrieval like searching databases, and in some decision support systems.
Okay. The paper used figure 4 to break down 3 main characteristics. What were those again?
Right. Figure 4 is helpful. It highlights 3 core characteristics: autonomy, task specificity, and reactivity adaptation.
Let's take them one by one. Autonomy.
Autonomy basically means that once you set them up and give them a goal, they can operate independently with minimal human intervention.
So set and forget, almost.
To a degree, yeah. Think of a customer support bot handling common queries without needing a human agent every time. Or a scheduling assistant that finds times for meetings based on everyone's calendars without you having to check manually.
Makes sense. What about task specificity?
This means AI agents are usually designed for quite narrow, well-defined tasks. They're specialists, not generalists.
Oh, okay.
So you might have an agent that only filters your email, or one that only queries a specific database, or one dedicated only to coordinating your calendar. This focus helps them become very effective at that specific job.
And the last one was reactivity and adaptation.
Right. This is their capacity to respond to changes in their environment. That could be a user giving a new instruction, something changing in the software they interact with, or getting a response back from another system.
And can they learn?
In some cases, yes. Some agents have a limited capacity to learn through feedback, helping them improve their performance over time. Think about how online recommendation engines gradually learn your preferences, or how a chatbot might learn which answers are most helpful for common questions based on user rates.
Okay, so what's the underlying tech? What's the brain making these agents work? The paper mentioned foundational models.
Yes, absolutely. The big leap forward for AI agents really hinges on these powerful foundational models, specifically large language models, LLMs, and increasingly large image models, LIMs, or even multimodal models.
Right.
These act like the core brain and sometimes the eyes of the agent, giving them the ability to understand complex information and make reasoned decisions.
So LLMs like GPT-4, they handle the language side, understanding questions, generating text.
Exactly. Models like GPT-4, PaLM, Llama, they've been trained on just vast amounts of text data. So they're incredibly good at understanding natural language requests, planning steps, summarizing information, generating human-like responses.
So an AI customer service agent uses an LLM to understand my complaint, maybe figure out it needs to check my order status, query that system, and then write me back.
Precisely. It uses the LLM for that understanding, planning, and response generation.
And LIMs add the visual element, like understanding pictures.
That's right. Large image models, or multimodal models like CLIP or BLIP2, they're trained on both images and text. This allows agents to perform tasks involving vision, like classifying images, detecting objects within them, understanding the relationship between an image and a description.
That seems crucial if the agent needs to interact with the real world or even just understand visual data.
Definitely.
Yeah.
Think about robotics, self-driving cars, or even analyzing medical images. Visual understanding is key.
The paper had that drone example inspecting an orchard. How did that work with these models?
Yeah, Figure 5 is a nice illustration. You have a drone equipped with an AI agent that's flying over an orchard, taking pictures.
Okay.
Using a limb, the agent can analyze those images in real time to identify potential problems, maybe diseased fruit or damaged branches.
And then?
If it detects an issue, it can automatically trigger an alert, maybe send the image and location data to a farmer or log it for inspection, all without a human having to constantly monitor the video feed.
That's pretty powerful.
It is. And the paper also points to related research, like giving robots more embodied understanding, using natural language to generate action plans for drones, using deep learning for aerial robotics. It shows how these different pieces are converging.
And getting access to these powerful models, the LLMs and LIMs, is it hard for developers building agents?
Actually, it's become much more accessible. Often, these foundational models are available via cloud-based APIs, application programming interfaces.
Like from OpenAI or Google?
Exactly. OpenAI, Google Gemini, Anthropic, Hugging Face hosts many. Companies offer access, so developers building AI agents can leverage these incredibly powerful models without the immense cost and effort of training them from scratch.
That must speed things up hugely.
It does. And there are also frameworks like LangChain or AutoGen that provide tools to help structure and manage how these models operate within an agent system, making development faster and maybe a bit easier.
Okay, so stepping back a bit, we had generative AI, first the ChatGPTs, the Midjourneys. You said they were a precursor but had limitations. What exactly held them back from being true AI agents?
Right. The paper points out that while generative AI is amazing at creating content, it's fundamentally reactive. It responds to your input, your prompt, but it doesn't have its own autonomous goals or the ability to orchestrate a multi-step plan to achieve something complex on its own.
So it always needs that next prompt from a human to keep going.
Pretty much, yeah. Some key characteristics of pure generative AI. It's input-driven. It does something when prompted. It can be multimodal work with text, images, audio. Code examples like GPT-4, PaLM, BLP2 show this.
But it doesn't remember things.
Not inherently, no. It's often described as stateless. It doesn't maintain a persistent memory of past interactions or a long-term plan unless you specifically engineer that around, maybe by feeding conversation history back into the prompt. It lacks that internal thought process for sustained, goal-directed action.
So it couldn't, say, autonomously plan my entire vacation from start to finish, find flights, book hotels, build an itinerary based on my preferences across multiple steps.
Not really on its own as a pure generative model. It could generate text about vacation spots or text that looks like an itinerary if you prompted it well, but it couldn't independently interact with booking websites, use those tools, make the reservations, and manage the whole process dynamically.
Ah, okay.
Couldn't really act on the world or use external digital tools autonomously. And that limitation, that gap between generating responses and actually getting things done in a dynamic environment is really what led to the development of tool-augmented AI agents.
And the large language models, the LLMs, they are really the engine making that leap possible from just generating it to actually doing.
Absolutely. The paper really emphasizes this. The progression from those reactive generative models to AI agents that can act with purpose, pursue goals, is powered by using LLMs as the core reasoning component, the brain, within these agent architectures.
So they're doing more than just language processing now.
Much more. These models, originally designed for language tasks, are now being leveraged for planning, for decision-making, for understanding context, for figuring out the steps needed to achieve a goal.
So they're actually doing some form of computer thinking or planning.
In a way, yes. They take the overall goal you give them, they interpret it, they try to break it down into steps, they figure out which actions to take, maybe which tools to use, and manage the workflow. The paper mentions AutoGPT and Baby AGI, again, as examples where the LLM acts as this central controller, deciding what needs to happen next.
And this is where that idea of tool-augmented AI agents becomes really important, giving the LLM access.
Exactly. This is a crucial development. To overcome some inherent LLM limitations like making things up, hallucinations, or having outdated knowledge because their training data is static. AI agents are being equipped with the ability to use external tools.
Like what kind of tool?
Could be anything, really. Accessing web search engines for real-time information, running code execution environments, interacting with databases, calling APIs of other software applications, sending emails, controlling smart devices.
Okay, so how does that work? How does the agent decide to use a tool and actually use it? The paper calls it tool invocation.
Right. So the agent, usually driven by the LLM's reasoning process, recognizes a point where it needs external information or capability. Maybe it needs the current weather, or needs to calculate something complex, or needs to book that flight. It then generates a specific request, often a structured call to an API, basically telling the tool what it needs. It formulates the right command or query for that external system.
And then the tool does its thing and sends the answer back.
Precisely. The tool executes the request, performs the search, runs the calculation, makes the booking attempt, and sends back a result or response.
And the agent understands that response.
Yes. That result is then parsed and fed back into the LLM's context or reasoning process. The agent integrates this new information, reflects on it, sees if it helped achieve the goal or sub-goal, and then decides on the next step.
So it's a loop. Think, act, use tool, observe result, think again.
Exactly. The paper mentions the React framework reasoning and acting. That's a prominent example of this iterative loop. The LLM alternates between generating internal reasoning steps, chain of thought type stuff, and generating actions, like tool calls, based on that reasoning, using the observations from the actions to inform the next round of reasoning.
The paper gave some examples of these tool-using agents. What kind of tasks are they tackling?
Yeah, we're seeing some really interesting applications. Agents like AutoGPT attempting market analysis by autonomously searching the web, synthesizing information, and writing summaries. In software development, tools like GPT Engineer or Aider using LLMs not just to suggest code, but to actually plan and execute the steps to build or modify software based on natural language requirements. And in research, you have systems like Paper QA that can intelligently search through vast databases of scientific papers using tools to find and synthesize answers to complex questions.
Figure 6 showed an example too, right?
Yes. Figure 6 illustrates a workflow where an agent needs to provide a real-time news summary. It realizes its internal knowledge is outdated, so it uses a search tool API to get current headlines, then uses its LLM capabilities to summarize those results, and finally presents the up-to-date summary. It shows that tool use in action.
Okay, so AI agents powered by LLMs and using tools are a big leap. But the paper suggests they still have limitations, especially when things get really complex or when you need different AIs to work together.
That's exactly the point the paper makes. While AI agents are powerful for many single-goal, relatively well-defined tasks, they often run into trouble with highly complex, multifaceted problems that require decomposition, long-term planning, and especially coordination or collaboration between multiple specialized capabilities.
And that's the gap that Agentic AI aims to fill.
Precisely. These limitations of single AI agents are what's driving the development and interest in agentic AI.
So what's the absolute core idea that makes something agentic AI? What's the defining feature?
Agentic AI is fundamentally about systems where Multiple, often specialized intelligent agents collaborate to pursue overarching goals.
Collaboration.
Absolutely. It involves structured communication protocols between these agents, mechanisms for them to share information or maintain a shared understanding, shared memory, and often dynamic role assignment or task allocation within the system. It's a conceptual leap from isolated agents performing tasks to coordinated systems achieving emergent outcomes.
It sounds, I don't know, much more like how humans tackle big problems, right? Different experts, different roles, communication.
That's a really good analogy. Key aspects of agentic AI often include goal decomposition, breaking down a large, complex goal into smaller, manageable subtasks, sometimes done by a dedicated planning agent. Multi-step reasoning, planning, and executing sequences of actions that involve multiple agents. Inter-agent communication agents, exchanging information, requests, or results. Reflective reasoning, maybe the system can evaluate its own performance or the group's performance and adapt. And memory systems allowing agents to learn from past interactions or maintain state over time as a collective.
The paper used a smart home analogy in Figure 7 to make this difference clear. Can you walk us through that?
Here, Figure 7 contrasts the two nicely. On one side, you have a single AI agent represented by, say, a smart thermostat. It perceives the room temperature, compares it to your desired setting, the goal, and takes an action, turns heating, cooling on/off. It's autonomous for its task, but isolated.
Got it. One job.
Right. On the other side, you have an agentic AI system managing a fully connected smart home. Here, you might have multiple specialized agents. One monitoring weather forecasts, one tracking your personal schedule, another monitoring real-time energy prices, maybe a security agent, a lighting agent.
A whole team.
Exactly. And they communicate and coordinate.
Yeah.
The weather agent tells the system a heat wave is coming. The schedule agent knows you'll be home late. The energy agent sees prices will spike in the afternoon. They work together to decide the optimal strategy, maybe pre-cool the house, using cheaper morning energy, adjust schedules. It's about achieving broader goals, comfort, efficiency, security, through collaboration, not just isolated tasks.
Okay, that makes the distinction much clearer. It's the difference between a single specialist and an orchestrated team.
Precisely.
The paper also had that table Y listing key differentiators. What were some of the main points there? Just to summarize the contrast?
Yeah, Table I is a useful summary. Contrast them across several dimensions. Definition: AI agent, autonomous software for goal-directed tasks. Agentic AI, system of multiple agents collaborating. Autonomy. AI agents have high autonomy for their task. Agentic AI systems have high autonomy for complex multi-agent operations. Task complexity. AI agents usually handle single sequential tasks. Agentic AI tackles complex, parallel, multifaceted tasks requiring coordination. Collaboration. Minimal or none for AI agents. Essential and core for agentic AI. Learning. AI agents might learn within their task scope. Agentic AI involves learning at both individual agent and system coordination levels. Applications. AI agents and chatbots, assistants, basic automation. Agentic AI aimed at robotics coordination, complex simulations, research automation, supply chain management.
Okay. And there were other tables too. Tables 2, 4. Did they add much more beyond that?
They go into finer grain detail, basically building out a broader taxonomy that also includes generative AI for comparison. They look at conceptual dimensions, key attributes, functional pipelines.
So things like
How are tasks initiated? Human prompt versus internal goal. How flexible are the goals? What's the time scale? Single interaction versus continuous operation. What kind of learning happens? How is coordination managed? What's the primary capability? Generation versus action. How far ahead can they plan? How do they interact? What's the core function, mechanism, structure, access to external data?
Wow. Okay, a lot of dimensions.
Yeah, it's a detailed breakdown. But the overall trend is clear. Moving from generative AI agents, agentic AI, you generally see increases in autonomy, complexity, collaboration, planning horizon, and interaction with the environment. Tables V through IX further dissect this across function, architecture, mechanism, scope, and interaction autonomy dynamics. It paints a picture of increasing sophistication.
Okay, so this progression isn't just in what they do, but fundamentally in how they're built, their architecture. The paper talks about this architectural evolution in Figure 8. How does the basic design change?
Right, Figure 8 shows this evolution nicely. A basic AI agent architecture typically involves core components like perception, getting input from the environment, reasoning, using the LLM brain to decide what to do, action, executing the decision, maybe using tools, and sometimes a basic learning component.
Pretty straightforward. How does agentic AI build on that?
Agentic AI architectures are significantly more complex. Key enhancements include ensemble of specialized agents. Instead of one agent, you have multiple, each potentially with its own skills or role. The paper mentions MetaGPT modeling different corporate departments as agents, advanced reasoning and planning. They might use more sophisticated techniques like the React framework we discussed, chain of thought, or even tree of thoughts for exploring different possibilities. Persistent memory architecture, crucial for collaboration and learning over time. This could involve different types like episodic, remembering past events, semantic, storing knowledge, often using vector databases. Autogen's use of scratch pads for agents is an example.
So they can remember what happened before.
Exactly, which is vital for context and consistency in long tasks or team efforts. And finally, orchestration layers, meta agents. These are components, sometimes dedicated agents themselves, responsible for managing the overall process. They might decompose tasks, assign them to other agents, monitor progress, evaluate results. ChatDev's concept of a virtual CEO agent overseeing programmer agents is a good example.
So it really is like going from that single skilled worker to a whole managed department or even a company structure in software.
That's a very good way to think about it, yeah. That orchestration layer is key to making the whole system work together effectively on complex problems.
Okay, we've covered what they are, how they evolved, how they're built. Let's talk concrete uses. What are some real-world applications of AI agents? Figure 9 gave an overview.
All right, Figure 9 shows AI agents being applied in several common areas. We see customer support automation, handling routine queries, providing information, basic troubleshooting via chatbots, internal enterprise search, helping employees find documents, data, or expertise within a company's systems, like Notion AI or Microsoft Copilot in some modes.
Okay.
Email filtering and prioritization, automatically sorting, classifying, and maybe summarizing emails to manage inbox overload, like in Superhuman or Features in Outlook Gmail. Personalized content recommendation, analyzing user behavior to suggest products, movies, articles like Amazon, Netflix, Spotify. Basic data reporting, automating the creation of simple reports or dashboards from structured data like Power BI Copilot or Tableau Pulse. Autonomous scheduling assistant, managing calendars, finding meeting times, sending invites, tools like Reclaim AI or older ones like X.AI.
And Figure 10 gave specific scenarios for use.
Yeah, Figure 10 provides nice little vignettes. 10A shows an e-commerce company using an agent for customer order queries and internally for HR policy. 10B shows email classification in a typical workplace inbox. 10Z has the retail platform recommendations and also a business user asking a BI tool agent for sales trends in plain English. And 10Z already depicts the scheduling assistant juggling meeting requests in a corporate setting. Table X in the paper also lists specific representative AI agent tools available around 2023-2025 and their primary functions.
Right, so mostly automating specific, often repetitive digital tasks. Now, what about the more complex applications of agentic AI? Where is that teamwork approach used or explored?
Agentic AI applications tackle problems requiring that collaborative element. The paper highlights areas like multi-agent research assistants, systems where different agents handle parts of the research process, literature review, data analysis, hypothesis generation, even drafting sections of papers or grant proposals. Autogen and Crew AI are frameworks used here. Figure 11A shows agents collaborating on a grant proposal.
Okay, that's definitely complex.
Intelligent robotics coordination, getting multiple robots, maybe in a warehouse, on a farm, or a swarm of drones to work together effectively, sharing information and coordinating actions to achieve a physical task. Figure 11B has that apple orchard harvesting example with multiple robots, collaborative medical decision support, envisioning systems where different AI agents specializing in, say, radiology, pathology, patient history, and treatment guidelines could collaborate to assist doctors in complex diagnoses or treatment planning, maybe in critical care settings like an ICU, shown in Figure 11's multi-agent game AI, creating more realistic and challenging non-player characters in games that exhibit complex group behaviors and adapt strategically. Adaptive workflow automation, automating complex business processes that involve multiple steps, departments, and decision points, potentially adapting on the fly. Examples mentioned include Multion or Cognosis aiming for complex web task automation, or cybersecurity incident response, where different agents analyze logs, identify threats, and suggest containment acts. Figure 11D.
Yeah, these definitely sound like tasks where just one AI agent wouldn't cut it. You need that coordinated effort.
Absolutely. They inherently require that division of labor, communication, and synthesis that defines agentic AI. Tables XY also lists some representative agentic AI models and frameworks from the 2023-2025 period.
Okay. Now, as with any powerful new tech, there have to be downsides, right? Challenges and limitations. Figure 12 in the paper breaks them. What are the main hurdles for the simpler AI agent? First.
Right. Figure 12 outlines some key limitations for single AI agents. A big one is still a lack of deep causal understanding. They're great at correlation, finding patterns, but often don't grasp the underlying why like humans do.
Okay.
They also inherit limitations from the underlying LLMs, things like hallucinating facts, being sensitive to prompt wording, sometimes exhibiting shallow reasoning, the cost and latency of running them, having static knowledge, less using tools, and potential biases baked into the training data.
Usual LLM suspects.
Pretty much. The paper also notes incomplete agentic properties. They might not fully exhibit all the ideal traits like proactivity, reactivity, social ability in all situations. Limited long-horizon planning and recovery is another. Complex, multi-step tasks that require anticipating things far ahead or recovering gracefully from unexpected errors can still be challenging. And finally, reliability and safety concerns remain significant, ensuring they consistently do what they're supposed to and don't cause harm.
Okay, those are quite a few limitations. And for agentic AI, where you have multiple agents interacting, do these problems get worse, or are there new challenges?
Both, really. Figure 12b highlights challenges specific to or amplified in agentic AI system. The causality challenges are amplified. Interactions between agents can create complex dynamics, distributional shifts, and potential error cascades that are hard to trace.
Like one agent's mistake messes up the whole team.
Exactly. Communication and coordination bottlenecks can arise. How do agents efficiently share the right information? How do they align on goals? What happens when they compete for resources? Designing effective protocols is hard.
Right.
There's a challenge of emergent behavior and predictability. Complex interactions can lead to unexpected, sometimes undesirable, system-level outcomes that weren't explicitly designed. Making them predictable is tough.
The black box problem gets bigger.
In a sense, yes, which leads to scalability and debugging complexity. Understanding why a multi-agent system did what it did, especially with opaque LLM reasoning, is incredibly difficult. Debugging is a nightmare.
I can imagine.
Trust, explainability, and verification are major hurdles. How can we trust these complex systems? How can they explain their collective decisions? Formal verification methods are lagging. Security and adversarial risks are also heightened. A compromised agent could potentially disrupt the whole system, or coordination mechanisms could be manipulated. And then there are significant ethical and governance challenges. Who is accountable when a multi-agent system makes a mistake? How do we prevent bias propagation across agents? How do we ensure alignment with human values? Finally, the paper notes immature foundations and research gaps. We still lack standardized architecture, robust theoretical underpinnings, especially around causality in these complex systems. It's still early days.
Wow, okay. That's a pretty sobering list of challenges for both types. But presumably, people are working on solutions. The paper talks about potential solutions and future roadmap in Figure 13. What approaches look promising?
Yes. Thankfully, research is actively tackling. Figure 13 outlines several promising directions for grounding and factuality, retrieval augmented generation, RAG, connecting LLMs to external knowledge source, for enhancing capability, tool-augmented reasoning, like function calling that we discussed, for better learning and adaptation, the agentic loop react of reasoning, action, and observation, for consistency and context, advanced memory architectures, episodic semantic vectors.
Okay, those help the individual agent. What about the multi-agent?
For agentic AI specifically, multi-agent orchestration with role specialization helps manage complexity. Reflexive and self-critique mechanisms allow agents or the system to evaluate and correct their own behavior. Programmatic prompt engineering pipelines offer more control and consistency than simple natural language prompts. Exploring causal modeling and simulation-based planning could help agents anticipate consequences better. Developing monitoring, auditing, and explainability pipelines is crucial for transparency and trust, and designing governance-aware architectures with built-in accountability and role isolation addresses ethical concerns.
So lots of active areas of research and development. Looking further ahead, what does the future roadmap in Figure 14 suggest for where these technologies?
Figure 14 paints a picture of continued evolution. For AI agents, the roadmap points towards becoming more proactive, anticipating needs rather than just reacting, deeper tool integration, and more seamless use of external capabilities, improved causal reasoning abilities, mechanisms for continuous learning from experience, and enhanced trust and safety.
So smarter, more capable, more reliable single agent. And for agentic AI?
For agentic AI, the future likely involves breakthroughs in multi-agent scaling to handle larger, more complex teams, developing unified orchestration frameworks to manage diverse agents effectively, more sophisticated persistent memory systems for shared context and learning, leveraging simulation for planning complex collaborative tasks, establishing robust ethical governance framework, and creating powerful domain-specific agentic systems tailored for industries like healthcare, finance, or manufacturing.
It really sounds like we're just scratching the surface, but on the verge of some potentially transformative advancement. Still lots of work to do on those challenges, though.
Absolutely. The potential is enormous for both paradigms, but realizing it safely and effectively means seriously addressing those limitations around reliability, predictability, explainability, and ethics.
Okay, so to try and wrap up this deep dive then, the core distinction we've unpacked. AI agents are generally single, autonomous software entities, often augmented with tools focused on specific goal-directed tasks.
Right.
Whereas agentic AI involves multiple specialized agents collaborating within a larger system, using communication and orchestration to tackle much more complex, multifaceted goals that a single agent couldn't handle alone.
That's a great way to summarize it, from the lone specialist to the coordinated team.
And we've seen how both have evolved rapidly, especially since the advent of powerful LLMs, and both have exciting potential applications.
But also come with a significant set of challenges that still need considerable research and engineering effort to overcome.
It definitely leaves you thinking, doesn't it, about how these different approaches might shape the future. Will we mostly interact with highly capable individual AI agents? Or will these collaborative agentic AI systems become the norm for tackling the really big problems?
It's a fascinating question. Maybe different problems will call for different solutions. It's certainly something to keep an eye on.
Indeed. And just before we sign off, one last reminder for you, our listener. If this discussion sparked your interest in learning more about AI fundamentals or applications,
Right, that course?
yeah, check out the AI course over at rogermanicum.com. And remember, you can use that discount code QPT for a special offer.
Good reminder.
Well, thanks for diving deep into the world of AI agents and agentic AI with us today. We really hope this exploration has helped clarify the differences and potential of these exciting and sometimes confusing technologies.
Yeah, hopefully cut through some of the hype and gave you a clearer picture.
We definitely encourage you to keep exploring this rapidly changing field. And hey, if you come across interesting sources or have topics you'd like us to tackle in a future deep dive, please do let us know.
We'd love to hear from you. Thanks for listening.